Hi, welcome back to my class in number 3. For today, we will take up the greatest common divisor of two integers. Let us now define the greatest common divisor of two integers denoted by A and B, elements of C, the set of integers, where A is not equal to 0 or B is not equal to 0. We read the definition of greatest common divisor. Let A and B elements of C. C here is the set of integers. Therefore, if A and B are elements of set C, A and B are integers. But there is additional condition that A is not equal to 0 or B is not equal to 0. Now, A and B cannot be both 0 because, as you will see later on, the greatest common divisor of A and B, if A and B are both 0, is 0. The greatest common divisor of A and B, denoted by GCD of AB. Greatest common divisor is defined as the largest integer, D, such that D divides A and B divides B. Based from this definition, the greatest common divisor of two integers A and B, where A is not equal to 0 or B is not equal to 0, but not both A and B are not 0, is an integer, and it is the largest integer that is a factor of both A and B. If the D is the largest integer that is a common divisor of A and B, then D is a factor of A, which means that B divides A, and D is also a factor of B, which means that D divides B. Now, by definition of divisibility, D divides A means that D is a factor of A, which means that A can be written as D times some integer K. Again, by definition of divisibility, when we say D divides A can be written as D multiply K. And similarly, if D divides B can be written as D times K, where K here is an integer. If E divides A and E divides B, then we call E the common divisor of A and B. And E here is also an integer. Now we define the set of all common divisors of A and B denoted by C, capital C of AB. We continue note number 2. We are given that E divides A and E divides B, and we call E a common divisor of A, the integers A and B, where A is not equal to 0 or B is not equal to 0. And the common divisor E here is also an integer. The set of all common divisors of A and B is denoted by capital C, C of AB. And this set of common divisors of A and B is defined by this using this set notation. It's the set of all integers E. The common divisors, the set of all common divisors of A and B is the set of all integers such that E divides A and E divides B. Again, the set of all common divisors of A and B, denoted by C of AB, is the set of integers E, such that E divides A and E divides B. And the greatest common divisor is the largest integer that divides A and B, and it's equal to the maximum of the set C of AB. The greatest common divisor of A and B is the largest, the maximum among the common divisors of AB. Or the greatest common divisor of AB is the largest of the element of the set C of AB, the set of all common divisors of AB. Now we consider the greatest common divisor of 0 and 0 with 0. In the definition earlier, we said that A is not equal to 0 or B is not equal to 0, which means that both A and B, which means that A and B cannot be both 0. So now suppose that A is 0 and B is 0. What would be the greatest common divisor of 0 and 0? Note number 3, by property of divisibility, as we have taken before, every integer divides 0. That is, d divides 0, where d is any integer. And this property says that everything divides 0. Every integer divides 0, including 0. We say that 0 divides 0. Because 0 can be written as 0 equals 0 times some integer k. Therefore, 0 divides 0. And this property of divisibility says that every integer divides every integer, d divides 0. So by this property, we say that all common divisors of 0 and 0 is the set of integers. Because every integer, every element of C divides 0, and every element of C, every integer divides 0. Therefore, the set of all common divisors of 0 and 0 is the set of integers. Now, the set of integers is an infinite set, which means that there is no largest element in this set. Therefore, there is no largest element that divides 0 and 0. And in this case, we take the greatest common divisor of 0 with 0 equals 0. Again, there is no largest integer that can divide 0 with and 0, since the set of integers, the set of all common divisors of 0 with 0, 0 and 0 is infinite. There is no largest integer that divides 0 and 0. But we define the greatest common divisor of 0 and 0 as 0. Now we take some examples. Our first example, consider the following. Find C of 18, 30. This is the set of all common divisors of 18 and 30. And we also find GCD of 18 and 30. The greatest common divisor of 18 and 30. The common divisor of 18 and 30 is an integer that can divide both 18 and 30. And one of these integers that can divide 18 and 30 is 1. 18 can be divided by 1, 30 can be divided by 1. Negative 1 is also a common divisor of 18 and 30 because negative 1 can divide 18 exactly and 30 is exactly divisible by negative 1. So two of the common divisors of 18 and 30 are plus and minus 1. Another common divisors, another two integers that can divide 18 and 30 are positive 2 and negative 2. 18 can be divided by 2 as well as 30 can be divided by 2. 18 and 30 can be both divided by negative 2 with 0 remainder. Therefore, 2 and negative 2 are another two common divisors of 18 and 30. Eighteen can also be divided by 3 and 30 can be divided by 3. Negative 3 can also divide positive 18. Negative 3 can also divide 30. Therefore, plus and minus 3 are another two common divisors of 18 and 30. Now, 18 cannot be divided by 4 exactly. Similar with 30, cannot be divided by 4 exactly. Also, negative 4 cannot divide 18 and 30 exactly. Therefore, plus and minus 4 are not common divisors of 18 and 30. 5 can divide 630, but 5 cannot divide 18 exactly. Therefore, plus and minus 5 are not common divisors of 18 and 30. Now, 6 can divide 18 as well as 30, and negative 6 can divide both 18 and 30 without remainder or with zero remainder. Therefore, plus and minus 6 are common divisors of 18 and 30. And these are all the common divisors of 18 and 30. Or this is the set of common divisors of 18 and 30. Any integer that is greater than or less than 6, greater than 6 or less than negative 6, cannot divide 18 and 30 exactly. Now, the greatest common divisor of 1830 is the maximum of the set, the maximum element of the set C of 1830. And by inspection of the set of all common divisors of 18 and 30, we see that the largest element, the maximum element of this set is positive 6. Therefore, the greatest common divisor of 18 and 30, the largest integer that can divide 18 and 30 is 6. For our example 2, consider the following. We want to prove that if the integer e divides a, then minus e divides a. If e here is an integer, then minus e is also an integer. The integers e and minus e are numerically equal, but they have opposite signs. And we start with the given e divides a. By definition of divisibility, we apply the definition of divisibility to the given e divides a. And by definition of divisibility, if e divides a, this means or this implies that a can be written as e multiplied by k for some k, where k is an integer. Now, using the fact that a is equal to e times k, where k is an integer, this implies that a is also equal to minus e multiplied by minus k, because negative times negative is equal to positive. Minus e multiplied by minus k is equal to ek. Therefore, this equation a equals ek implies that this equation is also true. Now, e divides a, and e is an integer. And a is equal to e times k for some k where k is an integer. Therefore, if e and k are integers, minus e and minus k are also integers. E and minus e are numerically equal but have opposite signs, and they are both integers. The integer k and the integer minus k are numerically equal but they have opposite signs, and they are both integers. Now, from this equation, we can conclude that minus e divides a, because we have shown that there exists some integer minus k, where k is some integer which we are sure exists because it has to exist, because a is equal to e times that integer k. So for some integer k, this equation must be true, and this equation ensures that there exists some integer k. So if this integer k exists, minus k exists. And because a is equal to minus e times minus k, we can conclude by definition of divisibility that minus e divides a for some, because there exists some integer minus k, such that a is equal to minus e times minus k. We therefore conclude that minus e divides a by definition of divisibility. So we have shown that if e divides a, where a is not equal to 0, as we have defined earlier in the definition of greatest common divisor, and e divides a where a is an integer, we have shown that minus e will also divide a. For our next example, consider the following. If a is not equal to 0, a here is an integer not equal to 0, or we say a is a non-zero integer. Then the largest positive integer that divides a is the absolute value of a. The absolute value of a is always positive, whether a is positive, 0, or negative. We know that from algebra, the absolute value of a is always positive. And the largest integer that divides a that is not equal to 0, a is an integer that is not equal to 0, is the absolute value of a. First, we showed that the absolute value of a divides a, where a is not equal to 0. If a is not equal to 0, then a can either be greater than 0, that means a is a positive integer, or a is less than 0, which means that a is a negative integer. Therefore, to prove that the absolute value of a divides a, we consider two cases. Case 1, where a is positive, a is greater than 0, and case 2, where a is negative, or a is less than 0. We consider case 1 where we let a greater than 0, which means a is a positive integer. Now, by property of divisibility, a divides a. This means that every integer divides itself. A divides a, that is, everything divides itself. If a divides a by property of divisibility, we apply the definition of divisibility to a divides a. By definition of divisibility applied to this fact that a divides a divides a implies or means that a is equal to a multiplied by k for some k where k is an integer. Now we let in case 1 a greater than 0, which means that a is positive. Therefore, if we take the absolute value of a, the absolute value of a would be equal to a if a is greater than 0, and that is by definition of absolute value. By definition of absolute value, the absolute value of a number a that is greater than or equal to 0 is equal to a. But in this case, we only take a greater than 0. And by definition of absolute value, the absolute value of an integer a that is greater than 0 is equal to a. And here, a equals a multiplied by k. We replace a at the right hand side of the equation with absolute value of a. So we write thus a is equal to absolute value of a multiplied by k. Now we have a is equal to absolute value of k, absolute value of a multiplied by k. And we are sure that k exists because this must be true for some k. That exists, we are sure that exists some integer k such that a equals a times k, because we know by property of divisibility that a divides itself. So if a is equal to absolute value of a multiplied by k for some integer k that exists, we can conclude from this equation that absolute value of a divides a. And this completes the case 1. where a is greater than 0. Now we consider case 2 where we let a to be less than 0, or we take a as a negative integer. For case 2, we now take a as a negative integer. Case 2, let a less than 0, which means that a is a negative integer. Then a can be written as minus a. We write a as minus a multiplied by negative 1. Negative times negative is positive. 1 times a is a. Therefore, a is equal to negative a multiplied by negative 1. But by definition of absolute value, if a is a negative integer, the definition of absolute value says that the absolute value of a negative number, is equal to the negative of the negative number. Therefore, if a is less than 0, negative, the absolute value of a would be positive. Because a is less than 0, that's negative, multiplied by negative, minus a would be positive. And so, in this equation, we now replace minus a with absolute value of a. And a is now equal to absolute value of a multiplied by negative 1. We have shown here that there exists an integer k which is equal to negative 1 such that a is equal to absolute value of a times k, where k is equal to negative 1. Therefore, we can apply the definition of divisibility, and we conclude that absolute value of a divides a if a is less than 0. Now, we combine the results in cases 1 and 2, and we simply say that absolute value of a divides a if a is not equal to 0. In case 1, we have shown that absolute value of a divides a where a is greater than 0. In case 2, we have shown that absolute value of a divides a where a is less than 0. And combining the results in cases 1 and 2, we conclude that absolute value of a actually divides a if a is not equal to 0. Now we go to the second part of the proof. We assume that there is another integer d that divides a, and d is greater than 0. By definition of divisibility, if d divides a, then a can be written as d multiplied by k for some k. But in here we can also take two cases for a is greater than 0 or a is less than 0. First, we apply the definition of divisibility to this d divides a. this is what we have. We are given D divides A, and to this we apply the definition of divisibility. And if D divides A, by definition of divisibility, A is equal to, must be equal to D times K for sum K. And we are sure that this sum K or integer K exists, because this equation must be true. A equals D times sum K, because we are given that D divides A. Now, if A is positive, then the absolute value of A is equal to A. And this becomes absolute value of A equals B multiplied by K. So from this equation, we can conclude that D divides the absolute value of A, because the absolute value of A, as we have shown, is equal to D times K for some integer K that exists. So from this equation, we conclude that D divides absolute value of A. Now suppose we take that A is less than 0, which means that A is a negative integer. Then the absolute value of A, by definition of absolute value, is equal to the negative of A. If A is less than 0, negative multiplied by negative, it becomes positive. Therefore, the absolute value of A, if A is less than 0, is equal to negative of A. But this equation is true. A equals D multiplied by K, because D divides A, can be written as minus A equals D multiplied by minus K. If you simplify this equation, it simplifies to this equation, which is true. And we write the negative here in K, because we take D as greater than 0. And we are sure that the sum integer K exists if K is an integer, so is negative K. Negative K is also an integer. If K is an integer, negative K is an integer. But minus A, if A is less than 0, its absolute value is equal to minus A, or minus A is equal to absolute value of A. In this equation, we replace minus A with absolute value of A equals D multiplied by minus K. And from this equation, by definition of divisibility, we conclude that D divides absolute value of A, where A is less than 0. Now, combining these two cases, a greater than 0, we conclude that b divides a, and a less than 0, we arrive at the conclusion that b also divides a. Combining these two, we simply say that b divides the absolute value of a if a is not equal to 0. A is not equal to 0 means that either a is greater than 0 or a is less than 0. But in both cases, we have shown that b divides absolute value of a. Now we apply another property of divisibility. In particular, we apply the comparison property for divisibility. If b here is greater than 0, and the absolute value of a, whether a is positive, greater than 0, or a is negative, less than 0, is positive. If b is greater than 0, positive, and the absolute value of a is greater than 0, positive, and we have shown that b divides a, by comparison property, we conclude that b is less than equal to absolute value of a. And from that, we will conclude that the absolute value of a is the largest positive integer that divides a, an integer a not equal to 0. State the final part of the proof. By comparison property of divisibility, if b is greater than 0, which is given, and the absolute value of a is greater than 0, which is true, because we know by definition of absolute value, the absolute value of any real number, in particular the absolute value of any integer, positive or negative, is always positive. And we have shown earlier that if a is not equal to 0, that is a either greater than 0 or a is less than 0, we have shown that b divides absolute value of a. And using this, by comparison property of divisibility, we conclude that b is less than equal to the absolute value of a. Now, from this statement, we can conclude that the largest positive integer that can divide a is the absolute value of a. Because if there is other d greater than 0 that divides a, then this number d that divides a is less than the absolute value of a. Therefore, the absolute value of a is greater than d, or d is exactly equal to the absolute value of a. So we can conclude from this inequality that the largest positive integer that can divide a is the absolute value of a. Now for your exercise, please try the following problems. Find C of AB. This is the set of all common divisors of a and b. And find GCD of AB. This is the greatest common divisor of A and B, where number 1, A is 21, B is 49. Number 2, A equals 16, B equals 32. Number 3, A equals negative 28, B is 14. Number 4, A is 42, B is negative 35. And 5 equals 5. A equals negative 112, B equals negative 116. And that completes our lesson for today on greatest common divisor. If you have a question about the lesson today, please ask your question in the comments below. But don't forget to subscribe to my YouTube channel, Art Calison, the channel of learning and leisure. Thank you for joining me in my class today in number theory.